Hi, my name is Jessica, and this is my advanced concept presentation number 5. Cellular respiration is a complex sequence of reactions to create energy from a single glucose. The whole process produces a net result of 30 ATP. To determine where each ATP comes from, we need to break down each step of cellular respiration. The first part of cellular respiration is glycolysis. The overall mechanism takes one molecule of glucose to create two molecules of pyruvate while also generating two ATP. Glycolysis occurs in two stages. The first stage has no ATP production, where glucose is trapped by hexokinase with the transfer of a phosphoric group from ATP to form glucose 6 phosphate, which is then isomerized to fructose 6 phosphate by phosphoglucose isomerase that can readily be cleaved into two 3-carbon molecules. This is then phosphorylated by ATP to fructose 1,6 biphosphate that is catalyzed by phosphofructokinase. So currently, 2 ATP have been used. In the second stage, the two 3-carbon fragments are oxidized into 1,3-bisphosphate glycerate by glyceraldehyde 3-phosphate dehydrogenase. This reaction transfers a hydride ion from an NAD+ to reduce it to an NADH, which actually generates two NADH due to the two 3-carbon molecules. This molecule can then be used to create ATP from ADP due to its energy richness. ATP is generated in this reaction, catalyzed by phosphoglycerate kinase when 3-phosphoglycerate is produced. Because actually two molecules of ATP are generated here, since stage 2 happens to both cleave 3-carbon molecules, it makes up for the 2 ATP used in stage 1. Next, 3-phosphoglycerate is converted into 2-phosphoglycerate in a rearrangement reaction of the phosphoric group by phosphoglycerate mutase, which is then catalyzed by enolase to create phosphoenol pyruvate. Lastly, pyruvate kinase catalyzes the reaction of the transfer of a phosphoric group from the PP to ADP to generate pyruvate and ATP. Again, 2 ATP are actually generated here, leaving us with a net product of 2 ATP and 2 NADH from glycolysis. Glycolysis is then followed by the oxidation of pyruvate to acetyl-CoA. This happens with the use of the pyruvate dehydrogenase complex, which produces CO2 and captures high transfer potential electrons in the form of NADH during 3 steps. The first step is decarboxylation, where the pyruvate is combined with a carbon ion of TPP to generate hydroxyethyl TPP, which is catalyzed by pyruvate dehydrogenase component E1. The next step is oxidation, in which the hydroxyethyl group of the TPP is oxidized to form an acetyl group and is transferred to lipoamide to generate an energy-rich thioester bond. The reaction is catalyzed by pyruvate dehydrogenase component E1 as well and creates acetyl lipoamide. The third step consists of an acetyl group being transferred from acetyl lipoamide to CoA, forming acetyl-CoA by dihydrolipoyl transacetylase E2, while the energy-rich thioester bond is preserved. Lastly, the oxidized lipoamide is regenerated by dihydrolipoyl dehydrogenase E3 so that another catalytic cycle can occur. In the process, 2 electrons are transferred to an FAD prosthetic group and then to NAD, ultimately generating an NADH. Because 2 pyruvate are converted into acetyl-CoA, 2 NADH are generated in this process, giving a product of 2 NADH in pyruvate oxidation. In total thus far, we have generated a net of 2 ATP and 4 NADH. The next step of cellular respiration is the citric acid cycle, which captures high-energy electrons from citrate and its metabolites to use the electrons to generate NADH and FADH2. This process occurs in two stages. The first stage consists of two carbon atoms being introduced into the cycle by coupling to oxaloacetate and forming citrate by citrate synthase. Citrate is then isomerized into isocitrate by aconitase, which is then oxidatively decarboxylated to alpha ketoglutarate by isocitrate dehydrogenase. This step generates an NADH as the first high transfer potential electron carrier in the cycle. Because 2-pyruvate are entering this cycle, 2 NADH are actually generated here. CO2 is then removed from alpha ketoglutarate to form succinyl CoA in a reaction catalyzed by the alpha ketoglutarate dehydrogenase complex, again generating 2 more NADH for a total of 4 NADH from stage 1 from both pyruvates entering the cycle. The second stage consists of the 4-carbon molecule being metabolized to regenerate oxaloacetate to continue the cycle. The succinyl CoA is an energy-rich thioester compound. The cleavage of the thioester from the succinyl CoA is coupled to the phosphorylation of ADP, catalyzed by succinyl CoA synthase, to yield succinate and an ATP. The succinate is then oxidized first to fumarate by succinate dehydrogenase. FAD is the hydrogen acceptor in this reaction, producing a molecule of FADH2. 2 FADH2s will be generated from both the pyruvates. Fumarate is then hydrated to malate by fumarase, which is then oxidated to form oxaloacetate by malate dehydrogenase. In this reaction, NAD+ is the hydrogen acceptor, creating 1 molecule of NADH, adding 2 more NADH to our net total. So after the citric acid cycle, we have 6 NADHs, 2 ATPs, and 2 FADH2s. In total thus far, we have 10 NADH, 4 ATP, and 2 FADH2. Next, we have oxidative phosphorylation and the electron transport chain, in which electrons from NADH and FADH2 are used to reduce molecular oxygen to water by a number of electron transfer reactions. NADH is oxidized by passing electrons to FMN, which is oxidized by the next electron carrier in the chain, and so on and so forth until they finally reduce oxygen. This electron transfer happens through a chain of 3 large protein complexes consisting of NADH Q oxidoreductase, Q cytochrome C oxidoreductase, and cytochrome C oxidase. Electrons of NADH enter the chain at NADH-Q oxidoreductase, or complex 1. The electrons flow from NADH to FMN and then through a series of 7 iron-sulfur clusters to Q. When Q accepts 2 electrons from NADH, Q2- is generated. This leads to the pumping of 4 hydrogen atoms out of the matrix of the mitochondrion. Q2- then takes 2 protons and is reduced to QH2. FADH2 is formed at complex 2, which is the succinate Q reductase complex. Succinate dehydrogenase, which generates FADH2 in the oxidation of succinate to fumarate, is part of this complex. The electrons from the FADH2 are transferred to iron-sulfur centers and then to Q for entry to the ETC. This complex does not transport protons. FADH2 enters the electron transport chain at Q cytochrome C oxidoreductase downstream from NADH due to the lower reduction potential, which yields fewer molecules of ATP than the NADH derived from the electron pump. Q-cytochrome C oxidoreductase complex 3 is the second proton pump, which catalyzes the transfer of electrons from QH2 to oxidized cytochrome C, then pumping protons out of the mitochondrial matrix. Cytochrome C oxidase is the last proton pump, otherwise known as complex 4. It catalyzes the transfer of electrons from the reduced form of cytochrome C to molecular oxygen. Next, ATP is generated by ATP synthase. ATP synthase and the ETC are linked by a proton motive force generated by electron transport, which consists of a chemical gradient and a charge gradient. The pumping of protons from the matrix to the cytoplasmic side of the inner mitochondrial membrane decreases the concentration of protons in the matrix. Protons will then flow back into the matrix to equalize the distribution, and this is the process of the proton motive force. ATP synthase is composed of the F0 subunit and the F1 subunit, which contains the catalytic activity of the synthase. The F1 subunit consists of the polypeptide chains alpha 2, alpha 3, beta 3, gamma, delta, epsilon. The active sites are on the beta subunits. F0 is a hydrophobic segment containing the proton channel. 3 active sites on the enzyme trap ATP and pi, ATP synthesis, and ATP release, and ADP and pi binding. The active sites can change functions, whether in the L conformation, which binds ATP and pi, T, which converts ADP and pi into ATP, or O, or open conformation, which can bind or release adenine nucleotides. This synthesis and release of ATP is driven by the rotation of the gamma subunit. The proton motor force drives the release of ATP from the enzyme. The proton flow through the F0 subunit drives the rotation of the gamma subunit, which promotes synthesis of ATP through the binding change mechanism previously described. Each 360-degree rotation of the gamma subunit leads to the synthesis and release of 3 molecules of ATP. The number of C subunits in the F0 subunit of ATP synthase determines the efficiency in which the proton gradient is converted into ATP synthesis, and because vertebrates have C rings composed of 8 subunits, about 3 protons are required for ATP synthesis. The electrons from NADH pump enough protons to generate 2.5 molecules of ATP, and FADH2 yields 1.5 molecules of ATP. Because the NADH generated in the citric acid cycle is already in the mitochondrial matrix, no transport is needed, whereas the NADH generated from glycolysis was created in the cytoplasm. These molecules cannot enter the mitochondria for oxidation by the respiratory chain, so the electrons from NADH, rather than the molecule, are carried across the mitochondrial membrane. The transport into the ETC is done by the glycerol 3-phosphate shuttle, which transfers a pair of electrons from NADH to dihydroxyacetone phosphate to form glycerol 3-phosphate on the outer surface of the inner mitochondrial membrane. An electron pair from glycerol 3-phosphate is transferred to an FAD prosthetic group to form FADH2, which ultimately results in 1.5 molecules of ATP being produced, rather than the normal 2.5 from NADH. So in total, we have 2 ATP and 2 NADH from glycolysis, resulting in a total of 5 molecules of ATP from glycolysis. 2 NADH were produced in the oxidation of pyruvate. The remaining 8 NADH from the rest of cellular respiration generate 20 ATP. The 2 FADH2 generate 3 ATP, giving a total of 30 ATP.